Okay, so let's dive right into this explainer. If you really think about it, a seed is basically a microscopic sleeping space capsule. I mean, it's this tiny, dry little thing, but it's completely packed with absolutely everything it needs to sustain life. It's just sitting there waiting for the precise environmental launch codes to finally ignite its engines.
And here's the game plan for our journey today. We're going to start with sparking the germination process, move into the science of seed dormancy, break down those specific dormancy levels, and wrap up with some really wild special cases and exceptions.
Part 1. Sparking the germination process, or as I like to call it, the launch codes. Let's look at exactly what tells a seed it's time to wake up.
So, to get things going, we need a very specific 4-step activation sequence. First up, water. Water literally swells the seed up and dilutes these internal chemical growth breaks, like something called abscisic acid, or ABA. Next, we need the right temperature to set the metabolic pace. If a seed wakes up too cold, it gets what we call imbibitional chilling injury. Basically, it goes into shock. Third is aeration. Just like us, the seed has to breathe, so it needs oxygen for respiration. And finally, for some seeds, light is that ultimate trigger. It hits these light-detecting sensors in the seed coat called phytochrome pigments, and boom, we have liftoff.
But what's absolutely wild is just how picky seeds can be about their launch conditions, especially temperature. They don't all want the same weather. You've got cool temperature-tolerant seeds, like your everyday carrots. Then there are seeds that actually require it to be cool, under 25 degrees Celsius, like delphinium. On the flip side, beans and okra demand warmth, needing it to be over 20 degrees. But here's the most brilliant one: alternating temperature-requiring seeds. These guys actually need a massive 10 to 15 degrees swing between day and night. It's a genius defense mechanism usually found in weeds and wildflowers, completely preventing them from sprouting prematurely just because of one weirdly warm afternoon in the dead of winter.
All right, moving on to Part 2, the science of seed dormancy. This is where we hit our plot twist.
So picture this. You've given a seed the absolute perfect amount of water, ideal warmth, plenty of air, and literally nothing happens. It just stubbornly refuses to grow. Why? Well, this exact mystery leads us to a plant's ultimate survival strategy: dormancy.
To really get this, we have to distinguish between a seed that's just taking a quick pause and one that is in deep, deep hibernation. Now, a seed is considered quiescent if it's just waiting out some bad weather. Maybe it's a little too dry or a bit too chilly. The second conditions improve, it sprouts. But if a seed is in true rest or true dormancy, its internal factors are actively slamming the brakes on germination. You could put it in a 5-star, perfectly controlled greenhouse and it still wouldn't budge.
Scientists break this down into 3 main types: ectodormancy, paradormancy, and endodormancy. But let's translate that into plain English. Ectodormancy, that's just bad weather, external factors keeping it asleep. Paradormancy is like being trapped in a locked box. The embryo inside desperately wants to grow, but a physical structure outside of it, like a really tough seed coat, is holding it hostage. And finally, endodormancy. This is basically an internal snooze button. The physiological conditions inside the embryo itself are just not ready to wake up yet.
That brings us to Part 3, breaking down dormancy levels. Let's look at the specific locks and keys needed to break out of this state.
First, we have to figure out when this lockdown actually started. Primary or innate dormancy is baked in from the very beginning. The seed acquires it naturally while it's still developing on the mother plant, but secondary or induced dormancy happens after the seed has already dispersed into the world. It usually gets triggered because the seed ran into absolutely terrible conditions, maybe extremely high salt, no water, or being buried in prolonged darkness, so it goes into full defensive lockdown mode just to survive.
Now let's look at the 3 main types of physical dormancy, those locked boxes we talked about. First, you have physical dormancy. Think of this as a locked, waterproof door. The seed coat literally won't let water in. Then there's chemical dormancy, which uses inhibitors like that ABA hormone we mentioned earlier. That's our internal chemical snooze button. And lastly, mechanical dormancy. This is exactly what it sounds like. A seed coat so incredibly thick and hard, it acts like an unbreakable shell, physically stopping the embryo from expanding.
But sometimes the problem isn't a hard shell at all.
Sometimes it's morphological dormancy, which simply means the embryo is immature. It literally just needs more time to develop its biological structures before it can ever sprout. And then we have physiological dormancy, which I find incredibly fascinating. This involves thermal and photodormancy. Basically, the embryo needs a highly specific sustained dose of winter chilling or an exact amount of light exposure to change its internal chemistry. It is nature's foolproof way of making sure a seed doesn't accidentally sprout on a warm autumn day, only to freeze to death a month later in the snow.
Finally, Part 4, Special Cases and Exceptions. Because right when we think we've got the rules figured out, nature absolutely loves to throw us a curveball.
Seriously, imagine walking through an orchard and seeing a seed actively sprouting roots and leaves while it is still hanging directly on the tree. No soil, no falling to the ground. That phenomenon is called vivipary. It is the exact opposite of dormancy, and it happens with certain seeds that simply never dry down or lose their moisture while maturing.
Mangoes are actually a fantastic example of this. They produce what we call recalcitrant seeds. When a mango drops its seed, that seed still holds about 50 to 60% moisture, and crucially, it won't dry down. If it doesn't sprout quickly, it dies. Now contrast that with orthodox seeds, like your common corn, wheat, or beans. Orthodox seeds are perfectly designed to dry out normally and enter that safe state of quiescence. You can literally leave them sitting on a shelf for years, and they'll patiently wait for you to plant them.
And for the ultimate survivalists out there, we have double dormancy. This is when a seed stacks multiple defense mechanisms at the exact same time. So it might have an inherited embryo dormancy, meaning it needs months of cold weather, plus a completely rock-hard physical seed coat that requires being broken down by soil microbes. You have to break these locks sequentially. It's exactly like trying to open a high-security bank safe that requires two completely different keys turned in the precise right order.
To wrap up this explainer, I really want to leave you with this thought. We've just seen how unbelievably precise this whole system is. Seeds are literally waiting for exact temperature swings, precise chilling hours, and highly specific moisture levels to unlock their launch codes. So, if global temperatures continue to shift unpredictably, how might a rapidly changing climate completely scramble those delicate codes? If our crops and wild plants start getting the wrong signals or no signal at all, it could disrupt this entire brilliant, fragile system that we literally rely on for our survival. It's an absolutely crucial piece of the puzzle to think about. Thanks so much for joining me today, and keep questioning the science all around you.